Don't clap yet. It might be terrible. You all thought you were escaping then, didn't you, for a moment? When Dirk's like, yeah, I'm closing this. You're like, thank goodness for that. I mean, I'm surprised so many of you withstood, I think that's the correct verb, isn't it? Withstood Michael's assault, also the correct term. That if you got through that, well done. You are amazingly hardcore to withstand Michael Hunger's 28 Things assault. I'm proud of each and every one of you for doing that. So it's lovely to be back in Berlin. It's an odd thing. I used to work here. Can you tell from my amazing German? No, there's a guy at the front here saying no. He may be looking at his phone saying no, but it was just an apt moment when he got me. He was like, no, I can't tell you. German sucks, Jimmy. Actually, I used to work over on Schönhauser Alley before it was invaded by hipsters, obviously. And so my last job before I joined Neo4j was here in Berlin. So it's kind of nice, right? Because Neo4j took me away from Berlin, and now it's kind of brought me back. So it's sort of, oh. Yeah, it's kind of a graph, right? It's kind of a shitty graph, but it's a graph nonetheless. So that's lovely. So I can't believe I'm going to do this to you after Michael's just given you the code hammer for the last 30 or 40 minutes. But I'm going to talk a little bit about computer science. Don't worry, it's going to be friendly computer science. It does exist, I promise. Don't let the academic stuff put you off. This is going to be humane. Right? Yeah, promise. So we're going to talk a little bit about computer science, and then also have a look at database architecture. Effectively, I'm going to hold open the curtain and let you look into how databases are built. It's going to be humane. Don't worry. And there'll be beer so you can drink and forget about it afterwards too. And then we'll talk about why the implementation and design choices in a database matter, what they mean for us as end users, people who have day jobs, right? Why should we care about how these things are built? And I'm going to impress upon you the importance of graph native technology. And in doing so, I will present you with some qualitative performance figures. So I hope to convince you that graph native is not only the most elegant and straightforward solution, but it also has performance advantages for you when you're trying to get your real jobs done, delivering systems to end users. Then we'll finish, and I'll show you that I do have an element of Berliner German by saying, für mich ein Pils bitte. Sound good? Come to Germany, they said. Friendly locals, they said. I know, right? So anyway, this is an artist's impression of how the next 40 minutes or so goes down. It's pretty accurate, to be honest. Thanks to my friendly Neo4j colleagues for doing that. That's nice of them. But we'll start off with a definition. So applied to data, native data formats or communication protocols are those supported by a certain computer hardware or software with maximal consistency and a minimal amount of additional components. And the last part of that's pretty important. Maximal consistency, minimum components. That is a useful working definition of native. And in fact, that's what I want to demonstrate to you today, that Neo4j meets this definition for graphs. That is that we have maximal consistency in what we do, nothing but graphs, top to bottom, and with the smallest reasonable number of components to achieve that job. So having planted that seed, I think you're ready for a little bit of computer science, right? Oh, the enthusiasm. Yeah, thanks, dude. I appreciate that. We've got an enthusiastic guy. Are you German? Bloody hell, times change. Computer science. So, would you? Really? Fine, whatever. Okay, bit of computers. Tough crowd, tough crowd. Come to Germany, he said. I know, right? Yeah. So we do a bit of computer science. Who remembers algorithms and data structures? Who loved it? Weirdos. Oh, yeah, it's the hardcore geeks over in the back corner there. So this is an unordered, singly linked list. Pretty straightforward stuff, right? But actually, it's got some really interesting properties. Well, I mean, really interesting in a computer science sense, not really interesting in the you would invite it to a dinner party sense, right? So you just need to level set a little bit. But it's got some really interesting properties. For example, if you wanted to add to this list, it's pretty cheap, right? You just add a head or tail. And because there's no ordering constraint, you won't ruin the data structure just by piling data in there. And so we say that in computer science, now having to justify my doctorate, I feel, in front of an audience, it's like a second viva. We say that that is constant time, or O1, big O of 1. It's the cheapest thing you can do in an algorithm, or a data structure. That's nice. But this list also has a slightly less desirable property, right? And it's for reads. And so if you've got a list like this, you know that if you're searching for an element in that list, or indeed you discover that an element isn't in that list, you typically have to read through many of them. And the larger the list, the longer it takes. And we call that order n, because it scales with the size of the list. So this isn't a bad data structure, right? It's actually pretty good for writes. And truth be told, there are bits of Neo4j that take advantage of that excellent write characteristic. So what could you do with it? You could turn it into a database, right? Now, don't get excited. Don't dash home and create linked list DB as your GitHub project. This is just a little bit jokey, okay? I'm not saying you should build this as a database. But if you did, if you wrapped an API around this, you could create a write-centric database. Yeah? It's a bit kind of awful for reads, but it's a database. I mean, you know there are some mechanical problems here, right? So you do have contention. If you have multiple clients trying to write in the database, you may have to guard the tail of the list there with a lock or something. But equally, we are aware of some ways of getting around that contention, right? So we know things like CRDTs, conflict-free replicated data types, would solve this. Effectively, each client writes into its own list, and then we merge the lists. So that's nice. So we've got a really nice way of creating a write-centric database. But remember, it's still awful for reads, right? So this suits one domain very well. It suits another domain much less well. So if you ever want to read from this database, be prepared for a very slow experience. Oracle, I'm sorry, just a bit of a cough there. Ooh. So I'm good now, don't need any water, it's okay. Cool. So I think we can tough up a bit now, right? We can, let's have a look at another data structure that maybe allows us to trade off this read-write decision that we have to make. And of course, in databases, we love trees. You probably had to study things like B trees and B+ trees at university. Databases love trees. And a tree structure might be, if I take my trivial tree structure, it might end up being something like this. Whoops. And in a classic database system, the non-leaf nodes of this tree would typically be in RAM, right? And they would provide an index, a in-memory index over the data in the leaf nodes, which would typically be on secondary storage on disk. It's kind of a classic old-school database setup. But if we thought about this data structure, we see that there are some really interesting trade-offs. So in order to be able to write to this tree, we have to find a leaf node, which means writes are no longer constant cost. In this case, this tree is pretty trivial, but we can approximate and say the cost of this is log n. And that means at each step, you throw away half of the possibilities. So for example, if the tree had about 1 million nodes, it might take 6 hops to find the place we're going to write. If the tree had 1 billion nodes, a US billion, it's the small billion, it might take, I see my American colleagues scowling at me now. Yeah, small billion, small billion. It might take 9 hops. If it was a real billion, of course, that would be 12 hops in order to find the place to write. Similarly, for reads, it's order, big O, log n for reads, which means in order to find something in the data structure, if you've got 1 million nodes in there, it might take 6 hops. Or indeed, if this is a real database, it might take 6 I/O operations on your disk in order to find that particular record. But what's nice about this tree is that it spreads the write surface. You're not so contended now around that one entry point into your data structure. So you can potentially have parallel writes going on here. That's nice, right? That's a nice thing. So we've seen these two things. Now, databases usually love trees. If you've suffered through database lectures, apart from you guys, if you had a lovely time in database lectures, you'll have seen this kind of things. Classic B trees arranged with an in-memory index and files and records on disk, and then B+ trees so you can do linear scans along the leaf nodes. And the thing is, if you're using B tree indexes, and I appreciate this pun works far better in English than German, you end up with lots of logs. That is, lots of log scale. Thanks, man. It's tough up here to hear just the slightest giggle. Remember, right, look, I work with Swedes, all right? This is a low baseline, right? How do you know an extrovert Swede? They look at your shoes when they're talking to you, right? So all we need to do is be slightly more happy than the Swedes, and this is a victory. Yeah, so just do me a solid. I'll make some shit jokes. You laugh at them. We're going to get through this far better than otherwise. Yeah, that's it. That's the spirit. Good lads and lasses. Well done. So if you've got these kind of B-tree indexes, you've got these kind of tree-based indexes, you get lots of log lookups. Normally, that's not a problem, right? Because log of 1 billion is way cheaper than 1 billion. So if I want to look up a single document over here or pluck out a single row over here, log cost seems like quite a reasonable trade-off. It's 6 I/O operations rather than 500 million I/O operations, right? That's quite a substantial difference. But in Neo4j, we don't have many logs. Yeah, the shit puns do continue. It's true. We don't have many logs. In Neo4j, as Kurt said this morning, we have this property of index-free adjacency. Typically in Neo4j, we only use indexes to find starting points in the graph at cost log n. From there on, we use constant time, O1 traversals around the graph to find your information goals. In fact, what we do is pointer chasing. It's the thing that these machines, including this extremely mediocre, overpriced laptop that they've given me, I know, right? If you've got an older MacBook Pro, keep it, clutch it to your chest, never let it go. These things are terrible. I'm being videoed. Apple know this. I'm in trouble. We don't do that many log cost lookups. So things tend to be very cheap. We're doing pointer chasing through the graph, which is both algorithmically and mechanically very inexpensive. So this is an important thing. The way that you choose to implement your database, its primary model, influences what it's good at and what it's bad at. So for example, in Neo4j, we engineer for graphs. That's all we care about. We love graphs. You might have got that sense during the day, perhaps. There was moderately, right? It may even seem, like some kind of like slavish cult to the graph, but that's us. If you decided to take some other model based on, expensive indexes, there's a disparity there. In Neo4j, 1 million hops might cost me 1 million I/O operations, 1 million pointer resolutions. In a billion-scale database, 1 million hops might cost me, oh boy, millions, that's log 6 million I/O operations? 12 million I/O operations for a billion scale? Uh-oh. It's suddenly got quite expensive, right? Because in a graph, the value is that you explore the data structure. You're not just picking a single element, a single document, a single row, targeting that finely. You're exploring the context of the graph. And if you've got a machine which is not cheap for doing those things, suddenly it limits you. And that's a worry, right? Because so many of the data problems we have today are all about connecting data and understanding that connected context. So your design and your implementation matter. my boss isn't here anymore, so I can say this because he's never going to watch this video. I have extremely high confidence that the modern database world is built by skilled engineers building great products, even those that aren't Neo4j, right? I even would go out on a limb and say that even Oracle is built by skilled engineers and it is a great product. Absolutely, I can attest to that. But when you try to exploit those databases for models they're not specifically engineered for, then you start to get in trouble. Ugh. That's a sea lamprey, by the way, that alien-looking thing. It's an invasive, non-native species in New York in the US, and it costs about $500,000 per year to try to control this in New York State alone. It's a metaphor. What I'm trying to tell you is non-native costs you $500,000 a year in waste. That's the subliminal message. Look, all databases have a native model, and as I said, I genuinely believe that they do an excellent job with those models. If I get Cassandra, I think it's going to be a great KV store. That's what Twitter tells me. If I get MongoDB, that's a great document store. That's what Twitter tells me. If I get Oracle, I'm richer than all of you because I can afford Oracle, but it's a great relational database. That's what Twitter tells me. Right? These are good databases. The reason that you will never get me to pour scorn on them because they are good databases built like people like me, right? You know, obviously, I'm clever enough to love graphs, but if I was slightly more limited in my intellectual outlook, I could be building those databases. But the evolution of those databases are driven by their primary workload. If you go and talk to some, MongoDB folks, they are going to espouse the love of documents the same way that I espouse the love of graph, right? They're not going to be as funny or charming or handsome, obviously, but they will do it. But evolution of that, of their implementation, of their design decisions, of their architecture, is driven by their primary workload. It's the dominant factor in their ecosystem. If you had some kind of bolt-on, it doesn't feel the love. The bolt-on will always get placed second fiddle, right? Because if there's ever a choice between something that works better for the dominant native model or something that works better for the graph, they're going to choose the native model. And you know what? I make the same choice in Neo4j every single day. If I have to choose between graph and something else, it's graph. Graph and document, graph. Graph and lunch, graph. Graph and see my family, often graph, remarkably, on the good days. So why are people getting into graph? Well, here's the reason. Holy moly. This is a chart, by the way, not a graph. Just putting that out there. It's like an inherited bugbear at Neo4j. Look at this. The top line there, the green line, is the growth of graph databases from 2013, around the point when Neo4j 2.0 came out, through to present day. And it consistently outstrips the growth of all other database types. From a small starting point, but nowadays, not so much. So if I was an organization that didn't have graph, and I was looking at this kind of motley crew of flatlining kind of growth, I'd be like, how do I get up there, right? If I was the CEO of another database company, I'd be like, no, we need to have that green line, right? How do we get there? That seems important to my shareholders and business value and other business things. So what do? Obviously, hold my beer, I got this. Said famous last words. Let's take a look at non-native architecture. So here we see a glamorous example of architecture. This is the Twisted Torso in Malmö in southern Sweden, which is Neo4j's HQ. You can see this is fake news, by the way. This is Sweden. Sweden never has blue skies. Never, ever. This is photoshopped within an inch of its life. But let's look at two architectural approaches that you might take if you were another kind of database that wanted to hold my beer and get on the graph bandwagon. So we see two approaches out there today. One of those is the graph layer. You take an existing database, an existing DBMS, you put a graph API on top of it, perhaps a third-party open source API, and declare victory. For what it's worth, I know that one doesn't work because the very first version of Neo4j was that. It doesn't work. The API looks graphy. The engine can't support graphs. You melt the engine. That's why we had to take the step of actually writing a native graph database management system. The second approach is to enrich your query language with some basic graph operators to extend its vocabulary such that it can try to speak graphs. So we can see how those things break out in a kind of side-by-side architecture diagram. So over here, Graph API talks nodes and relationships, or vertices and edges, whichever language you want. We then have a translation layer, which actually maps from the graph world that we like to perceive into the non-graph world, which is how the data is actually managed by the database. And it's typically a column store. On the graph operator side, we have a query language, which is made to work with the other store, say a document store in this case. And what we've done is kind of wedged in a graph operator from the side. Firstly, no Cypher. This is an important thing. Cypher is the dominant graph language today. Sure, it used to be a Neo4j thing, but now it's dominating everywhere. If you don't have Cypher up there, you've cut yourself off from an ecosystem of incredible graph people, graph tooling. You've cut yourself off from fantastic books like O'Reilly's Graph Databases. By the way, just putting that out there. Great, great book, great book. Fantastic book. Christmas presents, birthday presents, all fantastic, just steady on, steady on. Don't rush to get them yet. There'll be copies outside, I promise. So you've got no Cypher. That's a big downside because 80–90% of what goes on in graph data today is Cypher. On the graph layer side, the graph layer bit of code forces you to denormalize. You have to make some design decisions in there between how you map from the graph world that you're projecting through your API to the actual physical world of how your data is stored and managed. Often people there do diligent studies around how graphs look. And these people are, after all, graph experts. And they decide, well, what is a big, challenging graph? Anyone got any ideas what might be a big, challenging graph? I mean, half of you are already using it right now instead of paying attention to me, but something like Facebook, right? Yeah, it's a big, challenging graph, billions of nodes, that kind of thing. And we know from Facebook that we're only about 3 hops away from each other. That's amazing, right? So you take a well-studied graph with well-known properties, you say, right, we can denormalize for that. Facebook is one of the most challenging graphs in the world. If we can do that, then we're sorted. So actually, in that layer, I'll denormalize for traversals of depth 3, because that pretty much covers Facebook, which is the hardest graph on the planet. Right, kids? Sort of. Facebook is a big graph. The characteristics of the graph are actually quite trivial. It's a social graph. It's relatively shallow, 3 hops between any of us. It's well studied. It's well understood. How many hops are there if I wanted to phone Dirk right now between my phone and his? How many hops are there getting me back to my hotel, probably drunkenly, this evening? Well, I already got past 3. 4, 5. So the problem is when you've taken a very principled approach to design and you've chosen to denormalize, you're stuck with your denormalization. You're great for graph traversals up to 3 deep, and then you fall off a cliff for 4. That's nonsense, right? So many complex domains demand more than 3. They demand arbitrary, the ability to traverse at arbitrary depth. From 3 to 303, from 3 to 3,000, I don't know. Lots of hops, you need that horsepower. Meanwhile, on the graph operator side, you need a convention between your graph operator, this new piece of syntax, and the data you're storing. But because the database you're storing it in knows nothing about graphs, this is a user-level convention. By the way, congratulations. If you do this, you've just become a graph database implementer, like me. Yay! Because you're now in charge of keeping the graph intact and sane. Happy days. And you just thought you had a normal day job to do. No, you've now got 2 day jobs. As they say, suck it up, buttercup. At the bottommost layer of this stack, these things don't understand graphs. They can't prevent dangling relationships. They can't prevent logical, or in some cases, physical corruption. I have a proof coming out of column store corruption of graphs later this year. But basically, these systems don't understand graphs, so when things go wrong, expect logical and/or physical corruption. So in the graph layer, you've got these drawbacks. This is Japanese knotweed. It's an invasive species in the UK. If you have some in your garden, it has to be removed by specialists. It must be buried at a depth no less than 8 meters deep. If you have some of this in your garden, you cannot get a mortgage because it is going to destroy your house. In my previous house I lived in, my neighbors had this, and I fought a vicious battle with these evil plants to stop them coming into my garden, both chemical and physical and swearing. These are bad. These non-natives, they are bad. So look, the engine and store are not designed for graphs. Graphs are not the motivating workload. If there's ever a trade-off, if everyone has to say, I've got $1, do I invest it in columns or graphs? That dollar is going in columns. Always, because that's where the database makes its money for its vendors and provides most of its value for its users. Denormalization lets you down at depth 3 and so on. And then you've got a bunch of operational concerns, schema rigidity, evolution, so on and so forth. So if you're going to implement this, sit it on top of a column store. Column stores do exactly the wrong thing for graphs. Oh, that was a bit angry, flappy, wasn't it? Now I'm in the swing of it. So the thing is, what does a good hash function do? A good hash function spreads data around. What do you want to do when you're visiting a graph neighborhood? You want all of that to be local. So in one I/O operation, you retrieve a whole page, which hopefully contains the subgraph you're interested in. You don't have to do n lookups over the network because your hash function has been brilliantly engineered to do what hash functions do and spray your graph all over the bloody cluster. That was very John Cleese. Stop being John Cleese in front of these nice people. Also, by the way, you think this is order 1, right? You clever people. You're all like, yeah, but Jim, that's a hash map. That's O1. And we know that's not true. In a pathological case, hash maps are ON squared. They are deceitful. They're only O1 in the good times. When the good times fail, you are in trouble. Graph operator. Himalayan balsam, also a non-native species in the UK. I've got some of this in my garden. Fortunately, this one doesn't destroy your house, but it is rather rampant and blocks out native species. Works by convention only. That means when you're storing data in the database, you have to tag certain rows or documents with special metadata so that it can be picked up by the operator and then included in the graph. You guys are okay. You can do this. Right? That's not a problem. You're all proper professionals. But that other guy that you work with, he's going to come wading into your database and forget to put that metadata in there. And thereby, none of his documents are going to be available to the graph. It's a black hole. Moreover, if I remove a document from the graph, who remembers to go and remove all of the links that I put in the other documents to it? Oh, that's you guys again. Hey, did I welcome you just a minute ago to my job? This is now your job. Right, you have to do the job of the database because the underlying engine simply doesn't know about links. So it can't help you with that kind of referential integrity. It's designed for another job entirely. Moreover, it's probably built on B trees. So every time you want to hop, traverse a relationship, what are you doing? Go to the B tree index, log n, where n is the number of elements in the data set. Great, hop. Do the same again, do the same again. If I've got 1 billion nodes in my graph, that's 12 I/O operations per traversal on average. In Neo4j, that's 1 I/O operation per traversal on average, no matter how big your database gets. Constant time, even as the dataset size grows. So I think having developed this, this incredible intellectual hypothesis, that I think you should do one thing and do it well. And that's what Neo4j does. We've picked our thing. We think graphs are the most important thing in computer science, in software technology today. And we've decided that we're going to do that thing well. Got to tell you, we suck as a key-value database. Please go use another database for that. We suck as a document database. If that's all you care about, go find one, right? There are other document databases out there. But if you care about graphs, you're with us, because we care about graphs too. We want to do that one thing, and we want to do it really well. And we want to do it in a variety of processing contexts, right? So Neo4j originally was built for OLTP. We thought there was a lot of value and still believe there is a lot of value in being able to provide graph insight in between a web request, web response, that kind of fast online activity. One of my earliest exposures to Neo4j, long before I joined the company, was actually in this. It was in recommendations. And what used to happen in recommendations was that you would get recommendations given to you based on yesterday's information. You batch process overnight in Oracle or something. The problem with that is you get things that are stale. So you go into a shop, go into my supermarket, beep, beep, buy a PS4 or whatever, and then because of yesterday's stale data, you then print me out a voucher for 20% off an Xbox One. The psychologists that I worked with on that said that's called, they had a funny name for it, a contra-indicated recommendation. Contra, that's pretty Latin. We called it taking the piss, right? Because if there's nothing worse than you go into a shop, you buy something, then they're like, hey, suckers, you could have had this other thing much cheaper. Right? That's what they're telling you, right? That is what they are telling you. Now, what I also learned long before this, man, I'm a proper professor. I've got anecdotes. This is amazing. Arm patch is coming. I used to work at Toys R Us. True, not fake news. This dude's laughing his nuts off at me. It's true, man. It's true, I tell you. I'm great with kids. No, I'm not. But anyway, so when I did my training at Toys R Us, which was like a 1 hour watching a VHS video, calm down, youngsters. They'll be back in fashion soon in hipster Berlin. And it turns out that if you got a bad experience like this contra-indicated recommendation, you would go on and tell 17 of your friends and family about that poor experience, and then it would reflect, they would then choose perhaps not to shop at Toys R Us. And it was important to us as Toys R Us workers, elves, whatever we were called, to stop that from happening. Now imagine nowadays, like this was pre-Facebook, pre-Twitter, imagine what you could do nowadays. If you get a bad recommendation, a bad experience, you can still tell about 17 people because you're not more popular, but you just tell them faster on your phone, yeah? 17 people on your Twitter follower list worried about your Xbox recommendation. Great. So we want to do this. We want to do this because there's value in it, right? But we're also aware that you also want to do large analytic jobs. And traditionally, those things have been separate. ETL into OLAP cube kind of territory. But we don't really want to do that. So the kind of analyst name for this is HTAP, Hybrid Transaction and Analytic Processing. And it turns out that Neo4j does that quite readily. So since 3.1, with the causal clustering architecture, we've had the ability to split cluster roles. So we have these purple servers, what we call core servers, and they deal with transactions. Their duty is to keep your data super safe. And then we have these orange blobs, these read replicas, and their duty is to provide enormous graph workload scale. So far, so good. The read replicas may be milliseconds behind the transactional servers, but that's OK, because we impose consistency at a different layer. But what you can also do is then choose to hang off some OLAP servers off these read replicas, or indeed off the transactional servers. And now you've got OLAP data, analytical instances, which are not very far behind the real world. Milliseconds, seconds maybe if you choose. I did find someone in our history that wanted them to be 8 hours behind. Because they had to match an existing Oracle batch job. That was the most weirdest thing that I've ever encountered in my computing career. But indeed, you could then even choose to make those servers big, and multi-core, massive RAM, whatever you want. And the lovely thing about that is that it's the same cluster. There's no funky stuff going on here. There's no crazy ETL to cube. It's just run a Neo4j cluster, name your instances appropriately, and the Neo4j drivers will help guide you to the correct instance. So here we see, effectively, we're asking our driver up here to, using the bolt plus routing scheme, to go to a server which has the policy OLAP. And then down here, we've configured one of our servers to have the OLAP tag attached to it. That's all there is to it now. So if I want to launch something at an OLAP server, done deal. So now our separate OLTP and OLAP applications become one hybrid HTAP application with just minimal operational fuss. It's just a cluster. And the drivers allow you to send your analytics jobs over there and your online transaction processing jobs over there, and you don't have to worry about it, which is nice, right? Because you've got day jobs, and your day job isn't building a database. That's my day job. And post-Brexit, God knows we're going to need the jobs over on the island. So look, normally, the normal path through, feel sorry, that was a plea for clemency, by the way. Look, normally, the path through the stack is your application sends some cipher to the cipher query engine, and you do your pattern matching and get your insight. But of course, what we can also do is take a large graph, run it through some iterative graph algorithms to get some actions and insights. And as Michael pointed out in his extraordinarily information-dense session, you can do lots of useful algorithms. You can do centrality, you've got clustering or pathfinding algorithms, all of which, even though they're relatively simple algorithms, give you enormous insight into your data, even at actually extremely large scales. So now, our kind of stack, if you like, extends quite conveniently that we can send cipher both to the traditional cipher query engine or into the graph algorithms and gain insight either from matching patterns or by crunching the data through one of our algos. How do we do it? Well, we just use cipher to do it. Easy peasy. So, for example, we could PageRank. Michael showed you some PageRank. I'm going to show you some more. PageRank is about popularly connected nodes. So if you're a popular node connected to other popular nodes, your popularity gets multiplied. If you're a less popular node in the region of unloved nodes, your popularity gets diminished. Now, as you run the algorithm over this iteratively, you find that certain nodes grow in popularity, certain shrink in popularity. Now, if you're going to run this on a realistic data set, something like DBpedia, 11 million nodes, 116 million relationships, a typical scale-free graph, then you've got two choices. One, add to global warming. Right? Bring up an enormously glamorous Spark cluster, GraphX, all the machinery you like. Quick phone call to the local lignite mine because you're going to have to burn some kilowatt hours in this bad boy. It's okay, your neighbors have lignite, they'll flog it to you. Or do it on a single blade efficiently because we can exploit graph locality. No need for us to do big macho clusters of stuff. This modestly big graph, we can actually PageRank that in less than 10 seconds. Less than 10 seconds. That's pretty impressive. Good luck, by the way, even finding the Hadoop documentation in less than 10 seconds when you've already finished the work here. And what's important is that, not only is Neo4j able to conveniently combine OLTP and OLAP in the same cluster with no complex ETL and warehousing and that stuff, but it also scales down. Neo4j is super efficient. It's the most, it drives my sales guys crackers because what you can't do on a 3 or 5 instance cluster of Neo4j isn't worth doing. They want to sell you a 1,000 instance cluster of Neo4j. You don't need it. Sorry, dude. It's just the truth, right? You could even run useful stuff on Herr Armbruster's Raspberry Pi cluster, and we do. So we can scale down even to modest computing devices and get great value from it. But what does this mean to you? What happens when we actually look at the numbers? It's okay, Mr. Science, show us the data. Well, I can show you the data. That's cool. So Kurt showed you this morning, right? In Neo4j, we consistently benchmark our stuff. And we make sure that every release is faster, better, stronger than the last. That's what you'd expect, right? That's kind of what software should do. But we have another kind of benchmark that we run, which is asymptotic. Now, this benchmark was triggered by our CTO, Johan. He's a Swedish guy. And he was really angered, actually, by people saying, "Oh, does Neo4j scale? What can it do?" And he's Swedish, so I'll give you how he looked. Like, yes, I'm very angry about this. Maybe we should write a benchmark. His ancestors, the actual Vikings, are disappointed in him. Very, very disappointed. Very, very disappointed. So anyway, Johan, who remember was angry, wrote a benchmark, and it was a bit like this. We took a realistic retail data set from Amazon. We stuck it on a commodity dual Xeon processor server. So this is quite old hardware. This benchmark is probably 2 years old now. And we created a simple peer pressure recommendation system. This, by the way, reflects badly on all of you, right? Humans are rubbish. Basically, what this recommendation is, it says, "Oi, database, find me a pattern where you bought something that someone else also bought, and then tell me what they bought." You know this works on you. None of you needed the iPhone 10. You were like, I've got perfectly functional iPhone 6S. Then that guy come into the office with his iPhone 10. You're like, whoops, butterfingers. Now I need an iPhone 10. You are terrible beings. You are so easily influenced. I don't even need a Russian troll army to mess with you. I can just make you buy stuff by showing you what your friends have got. And then you feel compelled to keep up with them, right? So this is bad for humans, but in terms of database tech, quite interesting, right? So what we've got going on, single thread, 3 to 4 million hops a second, 10 threads, about 30 million hops a second, 20 threads, 50 million, and then we went asymptotic on 30 threads on this commodity piece of hardware, 60 million traversals per second. Even on this piece of hardware, which is mediocre and overpriced, do you remember that? I can do about 16 million traversals a second on a steady state database without breaking a sweat, right? That means I can explore a lot of graph very, very rapidly. In terms of read scale, we thought, well, okay, let's handle 1 trillion relationships, which we can do. Neo4j can address 400 quadrillion items. That's a really big number, right? That's even more than Emil's salary, just. So we did that. So we stuck 1 trillion relationships on a single server. It took about 33 terabytes on disk. And then we ran a compiled Cypher query on it, which was random reads. So effectively, we did small random walks through the graph. Even though most of the time we ended up hitting the disk because we only had half a terabyte of RAM compared to 33 terabytes of data, we still managed to sustain 100,000 user meaningful pieces of work per second. And that's pretty good, right? That is pretty good. What about write scale? Well, we could import the Friendster data set using actually software that's about to be deprecated. We import 1.8 billion relationships in 20 minutes. That's about 1 million writes per second in bulk import. Let me put this in big, bold numbers. You can do 1 million writes a second. You can do it on 10 to the 12 records, and you can do greater than 50 million traversals a second. Even when you switch Neo4j out of its bulk import mode and into transactional mode, you can still get thousands of ACID transactions a second through this laptop, right? Now, that's pretty good. You can achieve an awful lot with numbers like those. But you don't have to follow me on this path, right? You don't. You take the blue pill, the story ends, you wake up in your machine room next to your Oracle rack server, curled up into the fetal position, sobbing gently. It's fine. We can go that way. Or you take the red pill, you come with me, and we see how far these traversals go in the real world. So I saw some guys on the internet, and they had built a non-native graph database. They'd built a library, a graph layer, on top of a column store, Cassandra, actually. And they were really pleased because they'd done some benchmarks, and they got some new benchmarks that were better. Oh, wow, OK. Wonder what these guys on the internet are doing. That's interesting. So they got a benchmark. I have no idea just yet if that's good, bad, or indifferent. But that's quite a good cluster, isn't it? That's 6 machines, 48 CPUs, 256 gig of disk, 256 gigs of RAM. So that's about 300 CPUs, 1.5 terabytes of RAM, 1.5 terabytes of disk. For a 10 million node, 100 million relationship graph. Well, that seems a bit odd, because I think of that as a kind of test graph. That's the kind of small graph that I would use when I'm just doing a bit of local QA on my laptop. But maybe that's important. That's a lot there, right? 1.5 terabytes of RAM. OK. I wonder what Neo4j could do. Now, at one point, I did run these experiments myself, but it turns out that the one thing I can do as chief scientist is say, "Oi, Michael, hi, run these for me." And he does, right? He's super. Look, Michael's lovely, but bear in mind he was born and raised in the East, and he went to a school that didn't officially exist, and they experimented upon him. which means he doesn't sleep, he's amazingly clever, and also he's good at taking orders. He's basically a sleeper agent, right? Let's get that out of the way right now. I know there's a couple of you in the audience that are finding this uncomfortable right now because you're also sleeper agents, but like it's better to have it out in the open. So Michael ran these things for me on his home machine, not some fancy, you know, badass server, but Michael's home machine, and he sent me some numbers. Oh, thanks, Michael. So in Neo4j 3.3 on a single machine, oh, that's interesting. Count nodes less than 1 millisecond. So I don't know, but at least 200,000 times faster. Count relationships. Oh, less than 1 millisecond. Oh, okay, at least 200,000 times faster on a single machine, on Michael's machine, his home machine. He's probably also playing World of Warcraft while these are running, because you can't trust him for benchmarks. All right? Count outgoing rels at depth 2, so that's out and out. You know, about, what, an eighth of the time, something like that. Count outgoing rels at depth 3, still 20% quicker. Group nodes by property val, 8 times or so faster. Group rels by type, almost 8 to 10 times faster. Twice as fast counting knows and likes relationships. And then the one where you think Neo4j running on Michael's home machine while he's playing World of Warcraft should have been terrible at, it's 100 times faster. This is because Neo4j is efficient. Now, I talked to my engineering team about this. And they were like, yeah, obviously, Jim, because they're cleverer than me. They're like, obviously, Jim, that's always going to be the case. I'm like, oh, brilliant, I'll tell the audience on GraphTour. And they're like, no, Jim, you can't do that, mate. Oops. I'm like, well, why can't I do that? Well, because it's not a fair comparison. Bloody engineers, right? Bloody just... What do you mean it's not a fair comparison? Well, Jim, you know, it's been a while since you made any commits that actually made it past the build system, but let me tell you why. It's because in Neo4j, the reason that we do counts so quickly, for example, is because in the database system, in the DBMS, we have a count store. So we just look in the count store, and it tells us immediately how many nodes or relationships we have. Oh, OK. And so the other guys, what do? Well, they either traverse around the graph, or more likely, they do a brute force scan. Oh, OK, right. And it's the same for relationships. Yeah, of course it's the same for relationships. Like, how did you even get a job here? Oh, OK, fine. So it turns out that we had this conversation about all of these things. And then we got to PageRank, and they basically said, it's all about locality, stupid. So, OK, so I can't tell the audience this. No. Why not? Because it's not comparing, it's an apples to apples. This is apples to oranges. Neo4j is designed to do these things really quickly. You can't possibly tell them that. So I can't tell the audience that it's an apples to oranges comparison, but oranges are good for graphs. But oranges are good for graphs. Look at the numbers, people, right? If you get something that you care about, that you optimize for relentlessly every single day, yes, we're not doing slow, stupid things like brute force scans. We're actually engineering the whole of the database stack to be fast for this and only this kind of stuff, because graphs are all we do, and we want to do it well. So, just one more. You said they were friendly. It doesn't fly, does it? Fine, whatever. This is more my style anyway. Just one more thing. Just one more thing. Michael. Thank you for basically doing my job. I should really give you 10% of my salary as a gratitude. I'll give you the $5 later. Michael, bless him. He's like, hey, you should check this out. You're going to like this. So on a 6-core, 12 hyperthreads machine, 128 gig of RAM, Michael PageRanked the data from a very large payments provider. And what happened was, on that graph of 3 billion nodes, 18 billion relationships, 20 iterations of PageRank, that was completed in about an hour on one machine. That is pretty spectacular when you think about it. This is a large bit of payment data. So it's got amazing native graph performance. Why? Because all we care about is graphs, and we optimize every part of our stack: the query language, the query planner, the kernel, the disk format, the in-memory formats, the clustering protocol. Everything we do is motivated by the graph use case. And so because of that, you guys get amazing performance when you use the technology. Thanks, Michael. Yay. Woo, woo, woo. So we're going to have a suave drink. I would love for you guys to join us just next door for a cheeky little beer or two. It will be those, 1 litre monsters that you drink, I'm sure. Thanks for coming today. Drinks aren't on the 13th floor. They're on next door. Thank you, everyone. I hope you enjoyed the day.